Good evening, everyone. So today we are going to talk about attacking the Bluetooth low energy design and implementation in the mobile and wearable ecosystem. So I am Nitin. I work as a principal security analyst in DeepArmor, and he is my colleague Rahul. And DeepArmor is a cybersecurity consulting firm which offers services in vulnerability assessment, pen testing, secure SDLC designs, and also trainings and workshops. So for today's agenda, we are going to look into the blueprint of the IoT ecosystem, the challenges in this ecosystem, and also touch upon the topics of Bluetooth and Bluetooth LE security. And we have some demos of attacking the Bluetooth network over the air and also an ecosystem attack. And we'll be analyzing some traffic, BLE packets, and we'll conclude the presentation by giving a proposed solution for the problems which we have discovered. So this is how a typical IoT wearable ecosystem looks like. It has the cloud, which is the backend service, and it has the mobile phone, which is the smartphones, which we use to control the devices. It can have a gateway, which can be a physical device or a virtual device, which connects the nodes, modules, and other smart devices to the cloud. And we have node, which is the actual sensors of the environmental stats, and it could be a security camera, it could be a smart door lock, anything it could be in the IoT ecosystem. And all these components communicate with each other using HTTP, HTTPS for the cloud, and BLE, Bluetooth, NFC, Wi-Fi Direct, everything else for the rest of the components. So what is the requirement of a fitness tracker? Like it has to be comfortable because user will be wearing these devices and performing some physical activities. So there should not be wires hanging around. So this brings the need of wireless communication protocols, and these devices needs efficient onboarding, quick pairing, and needs continuous learning. So there are lots of data which is being captured and analyzed, and these has to be given to the user in the form of graphs, stats, etc. So these are the basic requirements. So let's look into the challenges in this ecosystem. So IoT ecosystem is constantly evolving, and the small and medium-sized firm worry about hitting the market shelves rather than worrying about fixing the security issues these days. So there are dozens of communication protocols, and without understanding or analyzing about it, it is being introduced into the ecosystem. So this itself is a weakness to the ecosystem. And there is long lives of this IoT products. For example, if I have a smart TV or smart refrigerator, I'll not be, as a customer, I will not be willing to hit the store every time there is a security issue. So all these has to be considered while developing the product. So if you take the technical problems, I would say first there are loads of data. Like there are PII, personal identifiable information, PHI, protected health information, geometric data, biometric data, and it can be transaction details, card details, everything is there. So there is loads of data, and processing all this data is a huge challenge in these wearable devices. And second one is the memory constraint. It has a very small software stack. So this itself raises a lot of problem in the ecosystem. And also in cryptography, like if you want to implement asymmetric cryptography or have a trusted execution environment, these are going to be heavy on these devices. And the third one is the cloud. Because they have multi-tenancy architecture. For example, if I'm the manufacturer of a device which is used by my competitors, like say Nike and Adidas, I have to store both these customers' data in the same cloud. So this cross-domain flow will lead to multiple exposure points as a consequence. So these are some of the technical challenges. So for today's agenda, we will be concentrating on BLE and Bluetooth. So these are wireless protocol, and everybody knows about BLE and Bluetooth, and it's widely used in all the wearable devices and in IoT ecosystem, like wireless headphones, speakers, even smart watches, and even healthcare systems are there and enabled with BLE as a protocol. And Bluetooth is used where the throughput is more and the range is less, and BLE is used where the power consumption has to be less and wider the range should be. So it is maintained by Bluetooth Special Interest Group. They own the licensing, and all the updates are given by the Bluetooth SIG. So let's jump right into the security of Bluetooth. So it all depends on the pairing. So there are 4 types of pairing. That is the just work methods, where your device might not have a display or buttons to enter a password or passcode, just like in our headsets. So this is just work methods where 6 zeros are used. And there is numeric comparison where same number has to be entered in both the device and the smartphone so that it gets paired. And the third one is passkey entry, where there will be a passcode which needs to be entered in the device to get it paired. And fourth one is out of bound pairing, where an external protocol is used to pair these devices. For example, NFC is used to pair the devices, like bump into each other, the device and the phone, the keys get exchanged. So once this pairing process is successful, the communication will be encrypted using AES 128. So there are some known weaknesses in Bluetooth and Bluetooth low energy. For example, the stronger the pairing algorithm, the stronger the communication is. So that always depends on the algorithms which is used. And there is key exchange, and it is always vulnerable to eavesdropping. And there is just work methods, which has by default 6 zeros. It is always prone to MITM, that is man in the middle attack. And also we bring the fourth one, that is the apps on the phones. We'll be discussing about this particular weakness in the further part of the slide. So first, let's look into the ecosystem problem. So I'm handing over to Rahul to give you the first demo.
Good evening, everyone. I'm Rahul. I work as security analyst at DeepArmor. As part of my job, I work on web app and cloud security, and I also spend a lot of time on fuzzing. So as Nitin explained, we'll be getting into demos now, where we have some recorded videos, and also I'll be showing a live practical demo. So as we saw previously, the problems and weaknesses in the Bluetooth IoT ecosystem. So now we'll be taking these fitness trackers as a classic example to demonstrate the challenges and problems that are there in the ecosystem. And we have responsibly disclosed the vulnerabilities that are there in this fitness trackers, and also it has been recognized by the manufacturers. So as you all can see, the golden one, which is a Fossil Q Dreamer fitness tracker, and the black one, which is a famous fitness tracker device, where these fitness tracker devices will be sending notifications and which calculates your step counts, calories, heart rate, and also send notifications to your mobile applications. So similar to the IoT ecosystem explained by Nitin previously, so this is specific to the wearable ecosystem, where it has a wearable device and mobile application and a cloud. So here the wearable device will be communicating with its mobile application via Bluetooth, that is using BLE protocol. And even sometimes the wearable device can talk to the cloud directly, and also the mobile application can talk to the cloud using HTTPS protocol. So for today's talk, we'll be mainly concentrating on the communication part that is happening between the wearable device and the mobile application. So this is how the data communication between the wearable device and the mobile application is happening. So as you all can see, there is a lot of data that is getting exchanged here. So from one side, whereas from mobile application to the wearable device, the data exchange will be mainly related, the data exchange will be like the mobile application sending commands for firmware updates, social app notifications, and even some wearable device are capable of accepting calls and replying to them. So this is on one side. So whereas from other side, from device to the mobile application, the data exchange will be mainly related to the activities that is going to happen there. And again, the social app notifications and many other data. So as we saw what are the data that are getting exchanged between the wearable device and the mobile application. Now I'm going to give a short intro on what is the problem that is there in this case here. So the traffic between the wearable device and the mobile application will be completely encrypted using LTK. So LTK is a long-term key where the traffic between the devices will be completely encrypted. And we'll be seeing more about LTK in the further slides. So at this point, whenever the attacker tries to steal the traffic or sniff the traffic between the devices, so he'll be ending up with the garbage data, that is the encrypted data. So where exactly does the problem resides here? So the problem really comes when there is a malware application sitting on your mobile on your mobile itself. So basically, what happens here is whenever the data from your wearable device reaches the Bluetooth layer, so the Bluetooth layer will decrypt the encrypted BLE data, and then it sends it to the mobile application in order to display the actual content of the data. So at this time, any applications which is sitting on your phone, so can sniff the traffic and get all the data that is getting exchanged between the wearable device and the mobile application. So this is where the actual problem resides here. So as we saw the problem now, so we'll directly get into the demo now. So for the demo part, these are the requirements where I'll be using a Xiaomi Mi Band 2, a fitness tracker, and I'll be using an Android phone. So on my Android phone, I'll be installing a legit application that is MiFit app. So where the Mi Band, the fitness tracker, will be connected. And then we'll be using a custom malware app, which is developed by DeepArmor. So these are the requirements that we need for the setup for the demo now. And this is going to be the overall overview of the demo, where I'll be showing you all how to intercept the traffic between the wearable device and the mobile application using a malware app. So as you all can see, to the left side, I have my Mi Band, that is the fitness tracker, so which will be constantly communicating with its mobile applications, where the data will be like step counts, calories, heart rate. So now in this case, what we are going to do is, as an attacker, we are going to sniff the traffic and steal step counts and calories using a malware app, which will be inside your mobile. So just like the other applications. So this is going to be the overall overview. So now let's directly get into the demo now. So before I start the demo, I'm going to explain the setup that I have over here for the demo, where I'm using a Visor application. So to the right side of my screen, you can see that I'm using a Visor application. So I've connected my Android phone to my laptop. So in order to share my mobile screen, I'm going to use the this Visor application here. So on my Android phone, I've installed the legitimate MiFit app that I'll be using for the demo. And this is the home screen of the legit application that I'll be using here. So this is the Mi Band 2, so the fitness tracker, which I'll be using for the demo here. So which is a tiny little device. So where this Mi Band will be connected to its legit application, that is MiFit app. So just to check, I'm going to see how the step counts and calories are increased here. So I'm going to simulate for step counts and calories. So right now the step counts and calories are 2274. So I'm simulating for step counts and calories using my MI band here. So as you can see, the MI band is connected to the MI Fit app. So the step counts are getting updated, as you all can see on the screen here. So this is fine. So till here, there is no problem. So everything is working fine now. So now let me introduce a malware app. So which will be sitting on my Android phone. So which will be sniffing the traffic and which will be stealing the step counts and the calories that the actual MI band is sending the data to the application here. So this is the malware app that I'm using for the demo here. So which is developed by DeepArmor. So this malware app is designed in such a way that it will be constantly listening to the different characteristics. That means the different UUIDs which are published by the MI band. So as you can see, there are different UUIDs that are present, so which are responsible for different activities. So mainly for today's talk, we'll be concentrating on the UUIDs, that is the universal unique IDs that are responsible for fetching the step counts and the calories here. So as I scroll down under this UUID 0000FEE, so you can see there are different UUIDs that are present. So the one which we are looking for is this one, the one that starts with 700003512. So this is the UUID that is responsible for fetching the step counts and the calories. So by doing lots of analysis and study, we were able to find out that these were the UUIDs that were responsible for fetching step counts, calories, and heart rate. So now I'll go back to my Legit application now. So before that, I'm going to explain one more application that I'm using for the demo here. So as you all can see to the left side of my screen, I'm using an Android Studio where I have connected my Android phone that I'm using for this demo here, and also the malware app, which I've selected the malware app that I'll be using for this demo here. So here, whatever the data that passes through the malware app, so all the log data will be displayed under this logcat window here. So basically what happens here is whenever the malware app sniffs the traffic and steals some of the data, so all the data will be displayed under this logcat window here. So now what I'm going to do is I'm going to take my MI band, the fitness tracker again. Again, I'm going to generate a traffic between the MI band and the legitimate mobile application, that is MI Fit app. Now let's see how the malware app will sniff the traffic and steals the step counts and the calories. So as you all can see, I'm simulating for step counts and calories again. So since both are connected, the actual data is getting updated in the MI Fit app, that is the Legit application. In the meanwhile, the malware app, which is sitting on the same Bluetooth channel, is able to sniff the traffic and get the step counts and the calories. So as you all can see, the step counts in the Legit application is 2353. So the same data, the malware app has been sniffed and it has got the same step counts here, 2353. So in the same way, now we can also sniff the traffic and get the heart rate as well. So now I'll go back to my malware app again. So the UUID which is responsible for fetching the heart rate is this one. So the one which starts with 180D. So under that, there is a UUID which starts with 28370000. So this is the UUID that is responsible for fetching the heart rate. So now I'll go back to the application, Legit application again. Now I'm going to use my MI band again in order to get the heart rate now. So I'm using my MI band to get my heart rate. So it is scanning now. So once the data is captured, so it will send to its Legit application. In the meanwhile, the data has been captured in the logcat window, that is the malware app as well. So you can see that the data is getting, it usually takes time to update in the actual Legit application. So you can see that heart rate in the legit application is 64. The same data that the malware app has been captured is also 64 over here. So in this demo, the malware app was able to sniff the traffic, and we were just talking about the step counts and the calories here. So now let's take an example where there is a BLE device, which is a blood sugar monitor device, which will be connected to a insulin pump. So these devices are mainly used for people who are diabetic. So just imagine if the diabetic patient with both the sensors and the insulin pump connected to an Android phone with this level of security, and let's say someone decided to install a malware app on the Android phone, which will monitor the blood sugar and which falsify the insulin pump. So this could be this is bidirectional, right? So this is not just about sniffing the traffic. It's about injection as well. So at this time, the malware app can send signals to send more or less insulin, so which could be really fatal here. So this was about the demo. So now let's get back to the slides again. So this is what we just saw in the demo, where we were able to sniff the traffic and steal the step counts and the calories that the actual legit MI band and the legit application was sharing here. And these are the GAD profiles that we just saw in the demo, where the left side screenshot shows the UIDs that was responsible for fetching heart rate, and the right side screenshot shows the UIDs which was fetching the step counts and the calories. So here, what is the root cause of this problem here? So the root cause of the problem here is any app on Android or iOS can read or write the data on this Bluetooth channel that the same legit application is writing. So that means that on Android, a malware app needs a Bluetooth or Bluetooth admin permissions, whereas on iOS, a malware app needs a core Bluetooth framework. So on the screenshot here, according to the SDK documentation, it says that any applications with Bluetooth or Bluetooth admin permissions are provided with extra abilities, where on the highlighted part, it says that those applications should not misuse those extra abilities here. So this brings us to the trust model. So in the demo which we saw just now, so there the trust model is built in such a way that the wearable device was trusting all the applications that was there inside my Android phone. So that could be your malware app or legit application or any applications that is inside your Android phone. So before we see the actual solution for this problem, so now we'll see how to attack BLE over the air. So now I'll hand over the session to Nitin to proceed further here.
Thank you, Rahul. So let's dive right into the over-the-air BLE attack. So as Rahul explained, we were able to see that we can install a malware app in your phone and steal the step count and calories. It can be step counts, calories. It can be your bank OTPs or your social messages, everything. So now we are going to sniff the data over the air without any contact to your phone or the device. We will be in the vicinity and will attack the environment. So we are going to concentrate on here, that is the Bluetooth and BLE over the air. So this is how we are going to do. So MI band is connected to the phone, and as an attacker, with the help of a tool, we are going to sniff this Bluetooth traffic from the vicinity. Like if we are in the same vicinity as the device and the phone, we will be able to sniff the data. So this is the Ubertooth 1 device, which is an open source Bluetooth testing tool developed by Great Scott Gadgets. And it is generally used for exploring the Bluetooth protocol. And we are using Wireshark network analyzing tool, and we are using Micrayon's Crackle, which we will see in the further part of the slides. So this is how the setup looks like. We have the phone and the MI band near the vicinity of the attacker, who is connected to the laptop. So a laptop with Ubertooth connected is the attacker, and we have the phone and the MI band app. So since typical conference has lots of Bluetooth device and gadgets, and the Bluetooth pairing happens in multiple channels, 37, 38, 39, due to the frequency hopping, we are not conducting this demo live. So we have recorded the session and we'll be showing it to you now. So what we are going to do is we are going to create a file that is a file pipe, in which one end of the pipe will be connected to Ubertooth device and the other end to the Wireshark, so that whenever the Ubertooth sniffs the Bluetooth data, we can see it live in the Wireshark tool. So once the Ubertooth is started, you can see a lot of data being sent. These are all the advertisement packets sent from our device. So once it is sent, you can also see that live in the Wireshark. So we have to ignore all these packets and stick to the packets which we want. That is the MI band pairing with the phone. So now we are going to apply filters to eliminate the advertisement packets, and we are looking for the connection request package, which is of PDU type 5, and it has and whatever Bluetooth that has data. So once we apply filter, and we are now pairing the MI band to the phone, and we are waiting for the connection request. So you can see that the connection request has been captured. Once it is captured, we can see lots of packets being followed by the connection request packet. And you can see that all these packets are not encrypted. It is the plain GAT characteristics and GAT profiles. Bluetooth attributes are visible here. So this MI band has not enabled LTK encryption. So we are able to see all the data. And the screen at the bottom, the white screen, is the app log. So we are going to compare, we are going to simulate some step counts and compare the step counts captured using Wireshark as well as, Ubertooth, as well as the actual app. So we understood that this particular step count and calories are being published in the handle 0040. And always the step count and calories has an offset in front of the packet, that is 0C. Once the hexadecimal value following the 0C are the step count and calories. So you can see that this particular packet 0C2A000, where 0C is the offset and 2A translates to, here it is. So 2A, which is 42 steps, and the calories burnt is 0 as of now. 40 and 0. So this is what we have observed from this Ubertooth. So the LTK encryption is not enabled, and we are able to see the packets as it is. So we are able to see the unencrypted BLE attributes, and we have found the step count and calories over the air. So this brings us to the topic of LTK, long-term key. So how this gets exchanged between the Bluetooth communication is as follows. So the device will be sending the pairing request, and the phone sends a pairing response. Then once it is exchanged, there will be a temporary key exchanged between the phone and the device. This gives us the SRAND and MRAND, random numbers generated. And with these three values, we will be generating a STK, short-term key. Once this short-term key is generated, this key will be used to encrypt the communication where the LTK will be sent. So this STK is used only for sending the long-term key. So once the LTK is negotiated between the device and the phone, the rest of the Bluetooth communication will be encrypted using LTK. So these are the steps: pairing request, response, then STK is exchanged, and after the exchange and agreement of long-term key, the channel is encrypted. So for this demo, we are it's going to be a screenshot. So for this experiment, we have taken Fossil Q Dreamer. It's not available now, and this is a simple accessory / activity tracker. Step counts and calories are given. So this device has enabled LTK, that is the long-term key encryption. So this is what we are going to do. We are going to capture the same pairing packets between the Fossil Q Dreamer and the phone, and we are going to get the packets which are supposed to be encrypted. So once we repeat the experiment, same capturing of the packets using Ubertooth, the packets you can see here, LL encryption request, LL encryption response, then start of encryption. Once the encryption is started, you can see that all the packets are L2 cap fragments. That is, it is all encrypted, and you are not able to see any other step count or calories or whatever data that belongs to the Fossil Q Dreamer. So does this mean is LTK is enough? Long-term key encryption is enough? So this brings us to the tool Crackle. So this is developed by Mike Ryan. Big thanks to him because it's an awesome tool. You should check it out. So this works on based on the exploiting the flaw in the pairing mechanism, where it brute forces or guesses the temporary key, then which leads to short-term key, then that leads to the LTK. So since the Fossil uses it doesn't have a display, it's using the 6 zeros just work methods. So let's see how this happens. So we have captured the Fossil traffic in a PCAP format, and we are sending sending this PCAP as an input to the Crackle tool. So you can see how quick Crackle can crack it because of the just work methods. Yeah, that's it. It has cracked the LTK key as well as the temporary key. You can see that the temporary key is 6 zeros, and it has found the LTK, and it has decrypted the packets as well. So let me show how the decrypted packets look like. So before in the Crackle, the encrypted packets were L2 cap fragments, and after it is passed to Crackle, we get the decrypted packets, which has all the Bluetooth attributes and attribute level GAT informations, and all the things are there in the Fossil. So this is what has happened. The first demo was sniffing over malware app inside your phone. The second one is about no LTK encryption, and you are able to sniff the traffic directly. And here in Fossil, LTK is encrypted. LTK encryption is enabled, but you are still able to decrypt because of Crackle tool. So does this mean is Fossil is broken? The answer is no, it is secured. So this is one of the fixes which gives us a solution for this problem as well. So what has happened there is, over the air, when we got the encrypted packets and when we passed it to the Crackle, we expect a decrypted packet with step counts and calories. But what we have received is decrypted packet, which is again encrypted with an application specific key. So because of this application specific key, the attacker will not be able to decrypt these packets, and it is encrypted in this fashion. This also solves the problem of malware attack inside your phone, because it all happens when it reaches your phone. LTK is decrypted and it's given to all the applications. Now the device understands who it is talking to, and it is the legitimate application. Only it has the key, and it can be decrypted only with the application specific key. So the problem trust model was this, that the device trusting the entire phone. Now the solution for this is the legitimate application only. to have the encryption and trust established between the device and the legitimate application. So the summary is that next generation IoT device has next generation problems, and the entire IoT security comprises of the device, phone, the communication protocol, cloud. So all these components has to be included in the secure development lifecycle process in the development phase itself. And there should be continuous security should be included in as a part of the CI/CD pipeline. And today the privacy is of bigger concern. So privacy, security, and legal has to be woven from the development cycle itself. So we also have to consider integration and interoperability problems while finding solutions to fix these problems. And it has to be considered to entirely secure our IoT ecosystem. That's it from us, guys. Any questions?
Yes, thanks for the presentation. In the last example, you told that the message were encrypted by the app.
Yes.
So how is the key exchange between the device and the app?
Yeah. So the key can be exchanged, like the device manufacturer can burn it inside the device, or it can be embedded in the key store, or once the device application is installed. So key exchange is the different process which has out of context for this, but it has to be exchanged. Okay.
Any questions?
Thank you for your presentation. Just a question about the encryption packet. Is it native to every application, or can you just like send raw text inside?
So you're asking about the LTK encryption?
The second, the application encryption. Yeah.
So it has to be from the application itself. It's not. It's like do not touch the entire phone. The encryption has to be enabled for my product, my device, from my application. Okay. So as a manufacturer, I have to maintain that boundary that I'm going to trust only my application. And we have to establish the app level encryption there.
So it's not native, like you can forget to set up the encryption for the application and the data could be intercepted?
So it cannot be intercepted because the key exchanges happen before the pairing process or even it is established. Okay. So over the air, we will not be able to sniff the application specific key because it is not exchanged in this process.
All right. Thank you.
Questions?
Yeah, thanks. So just kind of logical next step, how you can take the attack further. So with the application encryption now there, obviously the next step is the attacker with the malware. If you've got a malware app on the phone already, and if you're able to find, there's a few more technical prerequisites, I guess, but if you're able to access where the encryption key is stored, for example, if an attacker can get access to that, essentially you could theoretically still decrypt and do that. Like, are you considering exploring that deeper at all?
Yeah. It also depends on the Android's actual security, and you can consider that.
So it's not, it's secure for now, but it's still room for more improvement, I guess.
Yes, exactly. Okay, so if the keys are stored in somewhere in the app, and poor obfuscation can still be a problem in decrypting.
Other questions? Okay, perfect. So thanks again for the presentation. And
thank you.